Welcome back to the deep dive. Today we're opening up the hood on something that, might sound a bit dry dependency management.
Right. Sounds like paperwork.
Exactly. But it's actually, it's kind of the hidden stress fracture in a lot of modern software development, isn't it?
It really is. If you don't get it right, your app, it can quickly become a security risk or just a nightmare for build times and team collaboration.
Merge conflicts.
Yeah.
Yeah. So without smart dependency management, that beautiful app can crumble.
That's the core truth, yeah. Every single time you type import in Swift, you're basically pulling in external code. And with that comes external risk, external complexity. It's unavoidable, really.
So for anyone building in the Apple world, you're navigating this map, this landscape of tools, versioning, security traps.
Exactly. And our mission today is to take the material you've gathered and sort of map out that landscape. We'll focus heavily on Apple's official approach, the Swift Package Manager, or SPM.
Okay, and contrast that with the older tools, too.
Yeah, CocoaPods, Carthage, see where they came from. And crucially, look at the performance implications, the security stuff. What makes an app scalable versus fragile?
Oh, right. So let's start right there with the official answer. Apple's solution. What is dependency management fundamentally? And why did Apple feel the need to build SPM? What problems were they trying to solve?
Well, at its simplest, dependency management is just the automated way you get external code libraries, configure them, and link them into your project.
Before tools like this, it was manual.
Oh, totally manual. You'd literally download source code zip files, drag .framework bundles into Xcode, fiddle with dozens of build settings.
Sounds brutal.
Incredibly brittle, and repetitive, super error-prone. Apple saw this, realized the Swift ecosystem needed something unified, native, frictionless, built right in. That's the genesis of SPM. It was about controlling that experience, reducing that friction for developers adopting Swift.
Okay, so SPM, let's unpack that. You said it's more than just downloading code. It's deeply integrated. How does it actually work? What's its core function?
So SPM, it's Apple's official tool, not just for managing dependencies you use, but also for sharing Swift code you write. And the key is that integration, it's built directly into Xcode, into the Swift toolchain itself.
Right, you don't install it separately.
Exactly. You describe what your project needs, its components, its dependencies in a specific file, the package.swift manifest file.
Okay, the manifest.
And from that point, SPM takes over, it figures out the versions needed, fetches the source code, usually straight from Git repositories, compiles that code into modules, and handles all the complex linking stuff with your main app.
So it takes that whole configuration headache away.
Pretty much. It delegates all that error-prone setup to the compiler and the build system itself. It's designed to just work.
That sounds powerful. Now, inside that package.swift file, the sources you gathered mentioned a key distinction. .library products versus .executable products. Why is that separation important?
It's fundamental, yeah. It basically defines the purpose of the code package. A .library product is, it's a collection of reusable Swift code. Think of shared components like your networking layer, maybe some UI helpers or utility functions.
Things other code will use.
Exactly. The goal is to provide functionality to other programs or other parts of your app. It doesn't run by itself. The output is compiled Swift modules, maybe frameworks, that other targets can import and use.
Yes, it's building block.
Yeah.
Got it. What about .executable then?
And .executable product is the opposite, really. It's a standalone, runnable Swift program. This could be a command line tool you build, maybe a server-side application running on Linux, or even the main app target for your iOS app itself.
So its job is to actually run.
Right. Its purpose is execution, not just sharing code. The output is a single binary file that the operating system can launch directly. Understanding that difference is key to writing clean, modular package.swift files and structuring your project well.
Okay. The sources highlighted, I think, 8 key advantages of SPM. Let's walk through some of the big ones. It's described as official, native, and lightweight. That seems to address past issues directly.
Absolutely. Those first 3 points, they hit right at the historical pain points. Being official and native means it's built by Apple, fully integrated since Xcode 11. So right away, you eliminate the friction of needing separate tools, installing things with Homebrew, worrying if the manager itself will break with the next OS update.
You just trust that it works with Xcode.
Yeah. And then lightweight and fast. This is a big contrast to, say, CocoaPods. While CocoaPods was powerful, it added significant overhead. It modified project files, had its own dependency resolution logic, often leading to slower builds, especially clean builds. SPM's direct integration with the Swift compiler toolchain means it's much leaner. Dependency resolution is generally faster. Build times can be quicker.
And it's not just for iPhones and Macs, right? The third advantage mentioned was cross-platform. That feels strategic for Swift's future.
Oh, hugely strategic. This is probably the biggest advantage over CocoaPods and Carthage. SPM works great for iOS, macOS, watchOS, tvOS, but also for Linux and for server-side Swift projects.
Which the others didn't really handle.
Not natively, no. They were very much focused on the Apple device ecosystem. So if you're using Swift for back-end stuff, command line tools on Linux, SPM is the only official integrated way to manage dependencies. It really supports Apple's vision of Swift as a more universal language.
Makes sense. Now, thinking about the developer's day-to-day, the outline emphasizes simple setup and better Git integration. How does that translate into practice? What gets easier?
Simplicity comes from avoiding direct manipulation of the Xcode project file. You can add a dependency literally through a menu in Xcode file Swift packages, add package dependency. Or you just edit the package.swift text file.
No more dragging frameworks or messing with build phases manually?
Exactly. No manually tweaking linker flags or header search paths. It removes a whole class of potential errors.
And the Git part.
The Git integration feels very natural because SPM is designed around Git repositories. Dependencies are typically specified by their Git URL and a version requirement like a specific tag, branch, or commit hash.
So it uses Git's own versioning system.
Right. It encourages using semantic versioning tags directly in the repository. The source of truth for a version is right there in the Git history, making things quite transparent.
And that transparency leads to another point. No extra files. This sounds like a direct response to CocoaPods veterans.
Oh, absolutely. If you've ever battled a massive merge conflict in your .xcode proj file because two people ran pod install, you feel this one deeply.
Yeah, those project.pbx proj conflicts are legendary.
SPM avoids that entirely. It doesn't modify your .xcode proj file at all. The only significant file it adds to your repo is package.resolved.
What does that file do?
The package.resolve file locked down the exact commit hash of every single dependency, direct and transitive, that was used for a specific build. This is crucial for reproducible builds, ensuring everyone on the team and your CI server builds with the identical versions.
So no bulky pods directory, no separate .exe workspace file you have to remember to open?
None of that. Your repository stays cleaner, leaner. Fewer files means less potential for conflicts during code reviews and merges. It simplifies things. Okay, all of which points towards the seventh advantage. SPM is clearly future-proof.
Yeah.
Apple is investing heavily in it. They're constantly adding features. Like recently, support for binary dependencies, .exe frameworks was a big one, and huge improvements in handling resources.
Resources. Let's touch on that, because that used to be a nightmare, right? Getting images or strings out of a dependency.
Total nightmare. Frameworks used to have to do all sorts of bundle path gymnastics to find their own assets within the main application bundle. It was fragile. If the app structure changed, things broke.
So how does SPM handle resources like images, data files, localization strings now? This is the eighth advantage listed.
SPM standardizes it. Inside your package.swift, within a target definition, you declare your resources. You might use .process for things like images or .strings files that Xcode might optimize, or .copy for things like data files that should just be included as is.
Okay, so you declare them, but how do you access them in code?
This is the clever part. For each package target that includes resources, SPM automatically generates a special bundle reference called bundle.module.
Bundle.module. Okay. So in your package's code, instead of trying to figure out complex paths relative to the main app bundle, you just write, say, UI image named myImage in bundle.module compatible with .nil, and its localized string, myKey bundle, bundle.module, comment.
So the module itself knows where its resources are. Precisely. It guarantees the path is correct, whether that package ends up being built as a static library, a dynamic framework embedded in an app, or even used in a command line tool. It keeps the resources neatly organized, usually in a resources folder within the package structure, and just makes loading them reliable and simple. Big improvement.
Okay, so SPM sounds like a really solid integrated solution. But to appreciate why it's gaining traction, we need to look back at what came before, right? Contrast it with the tools developers used for years. Let's start with the big one, CocoaPods. What was its approach? Its integration philosophy. CocoaPods was, and for many Objective-C projects still is, the dominant player for a long time. It handles both Swift and Objective-C dependencies. Its core philosophy was essentially total automation.
Make it easy?
Yeah. Define what you need in a simple text file, the pod file. You list your dependencies, maybe specify versions, then you run pod install in the terminal.
And it does.
Everything. Or it tries to. It downloads the source code, sets up build configurations, links libraries, manages resources. It aims to handle the entire integration process for you. How does it actually integrate with the Xcode project, though? That seems like the tricky part.
That's where the complexity and sometimes the fragility comes in. First, CocoaPods historically relied on a centralized repository, the CocoaPods specs repo, which contains definitions for thousands of libraries. That centralization can be a bottleneck or a point of failure.
Okay. But the project integration itself, the big thing is, after running pods install, CocoaPods modifies your project significantly. It usually creates a new file, an .exe workspace file.
Right. And you have to use that file from then on, not your original .xcode prod.
Exactly. You must open the workspace. Because internally, CocoaPods has created a separate project for the pods themselves and configured your main project's build settings to link against them, manage header paths, all that stuff. It deeply intertwines itself with your Xcode project structure.
And that deep intertwining, that's where the infamous project.tbx prime merge conflicts often happen, right? That's the classic CocoaPods pain point, yeah. The project.pbx projfile inside your .xcode proj bundle is this massive, complex XML file that describes everything about your project structure and build settings. Because CocoaPods needs to modify this file to ensure everything links correctly if two developers add or update pods, or even just reorder files in Xcode differently.
Merge conflict.
And they are notoriously difficult to resolve safely. You're not fixing logic errors. You're trying to manually reconcile differences in UUIDs and complex build setting structures. One wrong move can corrupt the whole project file. So CocoaPods' philosophy is highly automated, handle everything, but the trade-off is that potential project fragility and the misery of merge conflicts. It can feel like a black box. Sometimes it works until it doesn't, and then debugging is hard.
Okay, so if CocoaPods is the heavy automation project modifying approach, the outline mentions Carthage as having a very different philosophy. What was Carthage about?
Carthage came about partly as a reaction against CocoaPods' complexity and project modification. It aimed to be much simpler, more lightweight, and less intrusive. Its philosophy is more hands-off.
Hands-off. How so? With Carthage, you also list dependencies in a file, this time called a cart file. Then you run Carthage update. But here's the key difference. Carthage primarily just fetches the source code for your dependencies and builds them into binary frameworks, .framework files, and that's it.
Pretty much. It stops there. It explicitly doesn't modify your Xcode project file or create a workspace. You keep working in your regular .xcode proj.
Cool. How do you actually use the dependencies then?
That's the hands-off part. You, the developer, are responsible for manually integrating those built frameworks. You literally drag the .framework files from the Carthage build folder into your project settings, specifically into the frameworks libraries and embedded content section.
Okay. So it gives you the compiled bits, but you wire them up yourself.
Exactly. It gives you control and transparency. You see the actual framework files, you manage the linking, but it requires manual steps, which can be forgotten or done incorrectly, especially by newer team members
who tended to prefer Carthage.
Often developers who were wary of CocoaPods modifying their project, or library authors who wanted a simpler distribution mechanism. People who valued control over automation. So the contrast is stark. CocoaPods high automation, potential project fragility, Carthage manual integration, project cleanliness, and SPM seems to be aiming for the best of both worlds. Native integration like CocoaPods, but without the project file modification, more like Carthage's cleanliness. That's a good summary, yeah. SPM tries to provide the automation and ease of use benefits without the intrusive project modifications and associated merge conflict risks, leveraging its deep integration with the Swift build system itself.
Okay, regardless of which manager you use, SPM, CocoaPods, Carthage, they all need a way to talk about versions. We touched on semantic versioning, Semver, that major-minor.patch format. Let's dig into what that really means for a developer specifying a dependency. It's more than just numbers, right? It's about managing risk.
Absolutely. Semver isn't just a numbering scheme, it's a contract. It's a promise from the library author about compatibility, and it's the core tool developers use to manage the risk of updates.
So break down the components again. Major, X 7.0.0. What does changing that first number signal? Major means breaking changes. If an author bumps the major version, say, from 1.7.2 to 2.0.0, they are explicitly telling you, warning, I have made changes that are not backward compatible.
Fair.
Like changing function names, removing features.
Exactly. APIs might have been removed, function signatures changed, core behavior altered in a way that will break your existing code if you just update blindly. Updating across a major version usually requires careful reading of release notes and potentially significant code changes on your end. The risk is high.
Okay, what about the minor version, 1.x0?
Minor means new features, but backward compatible. So going from 2.0.0 to 2.1.0 suggests new functionality has been added, maybe new classes, new methods, but all the old stuff from 2.0.0 should still work exactly as before.
So generally safe to update.
Generally, yes. It's usually a lower risk update. You get access to new capabilities without being forced to change your existing integration code immediately.
And finally, the PATCH version, 1.0.x.
Patch is for backward compatible bug fixes. Going from 2.1.0 to 2.1.1 means the author fixed some internal issues, maybe addressed a crash, improved performance slightly, or patched a security flaw, but critically, no API changes, no feature additions.
Purely fixes.
Right. This should always be a safe, low-risk update. Patch releases are about making the existing version more stable and secure. So how do dependency managers like SPM use this? If I see something like from 1.5.0 or maybe up to next major, 1.5.0 in my package.swift, what risk am I accepting? Okay, so from 1.5.0 is common in SPM. It means you're willing to accept any version from 1.5.0 up to, but not including, the next major version, 2.0.0.
So it allows minor and patch updates automatically.
Exactly. You're trusting the library author's adherence to Semver. You're saying, give me any 1.x updates starting from 1.5.0 because minor and patch updates should be safe.
But there's still a small risk if they mess up Semver.
There is. The alternative is to specify an exact version, like 1.5.2. That gives you maximum predictability. You know exactly what code you're getting, but it means you get zero automatic bug fixes or security patches. You have to manually update the version number every time.
So it's a trade-off between getting updates easily and guaranteeing absolute stability.
Precisely. Most teams opt for allowing minor updates from or up to next major for active dependencies and maybe lock down exact versions for more critical or less frequently updated ones. This whole idea of predictability, locking things down, it leads directly to the next concept. Reproducible builds. Why is this such a big deal, especially in the Apple world with App Store reviews and all that? A reproducible build is this idea that if you take the exact same source code, the exact same versions of all dependencies, which is where that package.resolve file is key, the same build settings, the same version of Xcode running on the same OS architecture, you should produce a binary output that is absolutely identical bit for bit every single time.
The antidote to, well, it works on my machine.
Exactly that. It's crucial for several reasons, especially for teams. First, consistency across environments. Your local machine, your teammate's machine, the QA team's test devices, your continuous integration CI server, they should all produce the exact same build from the same commit. This prevents wasting time debugging issues that only appear in one specific environment due to subtle differences.
Okay, consistency. What else?
Reliable debugging. Imagine a crash report comes in from a user running version 1.2.3 of your app. Using your version control and the package.resolved file from that release, you need to be able to check out that exact state and build an identical binary locally to reproduce the crash and debug it effectively. If the build isn't reproducible, you might be chasing a ghost.
Makes sense. You need to recreate the conditions precisely.
And finally, App Store submissions. This is critical for iOS. Apple reviews the binary you submit. You perform extensive testing, QA signs off, you archive it. You need absolute confidence that the binary tested is the exact binary being submitted. Any non-determinism in the build process, maybe something relies on the time of day, or file ordering changes randomly introduces a risk that the reviewed binary behaves differently from the tested one. Reproducibility ensures integrity throughout the release pipeline.
So that package.resolve file in SPM is really the linchpin for reproducibility, locking down those dependency versions.
It is. It records the specific Git commit hashes, not just the version numbers, ensuring unparalleled precision.
Okay, let's shift from versions and process to the code itself. How dependencies are packaged. The outline mentions static versus dynamic frameworks. This sounds like a fundamental difference in how code gets included and run. Let's start with static frameworks. What does static mean here?
Static means the code from the framework is copied directly into your main application executable file during the build process, specifically during the linking phase.
So it becomes part of the main app binary.
Exactly. Think of it like taking all the ingredients from the framework recipe and mixing them right into your main cake batter. When the build is done, there's just one single, larger executable file. There isn't a separate framework file that needs to be shipped alongside your app.
Okay, it's all baked in. What are the pros and cons of that?
The main pro is usually faster app launch times. Because all the code is already present in the main binary, the operating system's dynamic linker doesn't need to do extra work at launch to find and load separate framework files. It's simpler at runtime.
Simpler deployment too, presumably. No missing framework files.
Right, that's another pro. The main con is increased app size, potentially. If you use the same static framework in your main app and maybe an app extension, like a widget, the framework's code gets duplicated in both binaries. This can significantly increase the total download size of your app.
Code duplication.
Yeah. And the other con is that updating the static framework requires recompiling and redistributing the entire application or extension that uses it. You can't just swap out the framework file.
Okay. So when would you typically use static frameworks?
Often for smaller utility libraries or perhaps internal frameworks where launch time is critical and the potential code duplication isn't a major concern, SPM, by default, tends to build libraries statically.
All right, so if static is baked in, then dynamic frameworks must be different. How do they work?
Dynamic frameworks are kept separate. The framework's compiled code stays in its own .framework file, or .xc framework for multi-platform binaries. During the build process, the linker doesn't copy the code into your main app executable. Instead, it just records a reference, like a placeholder, saying, at runtime, you'll need to load this code from this separate file.
So the main app binary is smaller initially.
Yes, the main executable itself is smaller, but now you have to actually ship that separate .framework file inside your app bundle, usually in a framework's directory.
And the loading happens later.
Right. When your app launches, the operating system's dynamic linker, dialed, sees those placeholders. It then finds the corresponding .framework file within your app bundle, loads its code into memory, and resolves the links so your app can call functions within the framework. This loading happens at runtime or shortly thereafter.
Okay, so the pros here are likely the opposite of static. Reduced code duplication.
Exactly. The biggest pro is potentially smaller app size, especially if the framework is large or used by multiple components, app plus extensions. The code only exists once in the framework file, not duplicated. It also allows for, theoretically, updating the framework without rebuilding the entire app, though in practice with App Store submissions, you usually update everything together.
And the cons. I imagine that runtime loading has a cost.
It does. The main con is potentially slower app launch times. The dynamic linker has to do that extra work at launch to load and link these separate files. For apps with many dynamic frameworks, this can add noticeable delay.
And potentially more complex packaging, making sure the framework is correctly embedded.
Yes, you have to ensure the framework is correctly signed and embedded in the app bundle. If it's missing or corrupted, the app will crash at launch because the dynamic linker can't find the required code.
So when are dynamic frameworks typically used?
Often for larger, complex SDKs, think things like the Firebase SDK or large analytics suites. Also, historically, Apple pushed dynamic frameworks for app extensions because they needed a way to share code between the main app and the extension process without static duplication becoming unmanageable. The trend now seems to be shifting back towards static where possible for performance, but dynamic still has its place for very large modules or specific architectural needs.
Okay, we've got the building blocks, how we get them, SPM, etc., how they're versioned, Semver, how they're physically linked, static, dynamic. Now let's talk about where things get messy, especially in larger projects. The outline highlights transitive dependencies. What are these and why are they described as a silent killer?
Transitive dependencies are the dependencies of your dependencies, the code you rely on indirectly without explicitly listing it yourself.
So if my app uses library A,
right, and library A needs library B to function,
then my app implicitly depends on library B, even if I never mentioned B in my package.swift.
Exactly. Library B is a transitive dependency for your app. You get it pulled in automatically when you add library A.
Why is that a potential problem? Seems convenient.
It is convenient until it isn't. The problems arise mainly from conflicts and lack of visibility. The classic issue is the diamond dependency problem.
Okay, sounds ominous. What's the diamond?
Imagine your app is the top point of a diamond. It directly depends on two other libraries, say library A, left point, and library C, right point. Now, suppose both library A and library C also depend on the same underlying library, library B, bottom point.
Okay, so A needs B and C also needs B.
Right. Now, what happens if library A requires library B version 1.5, but library C requires library B version 2.0?
Conflict. The build system needs library B, but it's getting two different version requests for it.
Precisely. And since 1.5 and 2.0 are different major versions, they are likely incompatible according to Semper. The build system, like SPM or CocoaPods, can only pick one version of library B to include in the final build.
So either A breaks or C breaks.
Or the build fails entirely with a dependency resolution error. If it picks v2.0, library A might crash trying to call functions that changed or were removed. If it somehow picked v1.5, less likely with typical resolution strategies, library C would break. And debugging this can be a nightmare because you, the app developer, only explicitly asked for A and C. The conflict is hidden down in B, which you might not even realize you were using directly.
Wow. Okay, so transitive dependencies create hidden coupling and conflict potential.
Yes, and other issues too, like breaking changes and transitive updates. You might update library A to a new minor version, thinking it's safe, but if that version of A now pulls in a new major version of B, your build could break because of changes in B, even though you only updated A.
Yeah.
Also, hidden dependencies. If library B is suddenly removed as a dependency of A in a future update, but your code had somehow started relying on B directly, maybe through some leaky extraction, your code breaks unexpectedly.
This lack of visibility sounds like a direct path to security headaches, too. If we're inheriting code we didn't explicitly ask for, how does that play into security and compliance risks? The outline lists several. This feels critical.
It's arguably one of the biggest challenges in modern software development. Trusting your direct dependencies is hard enough, but you're implicitly trusting their dependencies too, and their dependencies. It's a chain. Let's focus on the most concerning one listed, supply chain attacks. What exactly is that? This is the nightmare scenario. Instead of attacking your company's servers directly, attackers target the software supply chain, the third-party libraries everyone uses. They might compromise the account of a maintainer of a popular open source library.
Click on GitHub.
Yeah, or NPM for Node.js, PyPI for Python, etc. Or they might contribute seemingly helpful code that actually contains a hidden backdoor. Then they publish a new version of this trusted library, say a patch release so it seems innocuous.
And developers just update.
Exactly. Developers run Swift package update or pod update, see a minor patch bump for some utility lib, and pull it in. But this new version contains malicious code, maybe designed to steal API keys from the build environment, siphon off user data, or install ransomware.
Wow. So the attack comes through the trusted dependency.
Precisely. It exploits the trust inherent in using third-party code. We've seen major incidents of this in other ecosystems. Trusting library A means you are implicitly trusting the security practices of library A's maintainers, their build systems, and everyone involved in libraries B, C, D that A depends on. It's turtles all the way down.
So every update is potentially risky. Does that mean we should be auditing every line of code and every dependency? That seems impossible.
It is practically impossible for most teams, which is why other risks become important, like relying on outdated or vulnerable libraries. If library B v1.5 has a known critical security vulnerability, a CVE, common vulnerabilities and exposures, and your dependency graph locks you onto that version, your app inherits that vulnerability.
Even if it's a transitive dependency you barely know about.
Especially then. Because you're less likely to be actively tracking library B's security advisories. You might keep library A up to date, but if A still relies on an old vulnerable version of B, you're still exposed. This is compounded by those transitive dependency risks. The hidden nature makes them harder to monitor and audit.
The list also mentions data privacy risks. How do dependencies play into that?
Some libraries, especially analytics or advertising SDKs, might collect user data or device information. If you pull in such a dependency, it might start collecting data in ways you didn't anticipate, potentially violating privacy laws like GDPR or CCPA. Your app becomes legally liable, even if it was the third-party code doing the collecting. You have to vet what data your dependencies access and transmit.
And license compliance risks. That sounds like legal trouble too.
Yeah. Open source licenses vary widely. Some, like MIT or Apache, are very permissive. Others, like the GPL or AGPL, have strong copyleft requirements. If you inadvertently use a GPL library in your proprietary closed-source application without fully understanding the obligations, you could, under some interpretations, be legally required to open source your entire application. It's crucial to check the licenses of all dependencies, including transitive ones. Okay, one last risk mentioned connects back to static versus dynamic. Build and distribution risks, specifically with pre-built binaries. Right. If you consume a dependency not as source code, but as a pre-compiled binary like in .xc framework that SPM now supports, you lose visibility. You are running code that you cannot easily inspect or audit.
You just have to trust the publisher didn't put anything extra in there.
Essentially, yes. You're trusting that the binary they provided corresponds exactly to the source code they claim it does, and that their own build process wasn't compromised. For organizations with high security or regulatory requirements, building dependencies from source is often mandatory to mitigate this risk of opaque binaries. You trade build time convenience for increased trust and auditability.
Okay, we've talked a lot about managing external code. Let's shift focus slightly to how we structure our own code, especially in large applications. The outline connects dependency management directly to internal architecture, specifically modularization. Why is breaking up your app into modules so important for big code bases?
Modularization is basically the opposite of having one giant monolithic code base. It's the practice of splitting your application into smaller, independent components modules, which could be Swift packages or frameworks. Each module has a specific, well-defined purpose, clear boundaries, and a public interface.
Like having a networking module, an authentication module, maybe separate feature modules.
Exactly. And the reasons this is crucial for scale are numerous. The outline lists 7 key benefits, but let's hit the highlights. The most immediate win for developers is usually faster build times.
How does modularization help with that? Think about it. In a monolith, if you change one line of code anywhere, Xcode often has to recompile a huge chunk, if not all, of the application. But if your app is split into, say, 30 modules, and you only change code inside the user profile feature module, Xcode only needs to recompile that module and maybe things that directly depend on it.
Precisely. Incremental builds become much faster because the scope of change is limited. We've seen teams literally cut their daily compile wait times in half or more just by aggressively modularizing their code base. It's a huge productivity boost.
Okay, faster builds. What about the code structure itself? Does it force better design?
Absolutely. That leads to better code organization and stronger encapsulation. Each module should group related functionality logically. And importantly, modules should only expose what's absolutely necessary through their public API. All the internal implementation details, helper classes, etc. stay hidden, marked as internal or private.
Preventing spaghetti code.
Yeah, it prevents Module A from reaching deep into the guts of Module B and messing with its internal state. This reduces tight coupling, makes the code base easier to understand and reason about, and makes changes within one module less likely to break unrelated parts of the app.
And reuse. Can you reuse these modules? That's another major benefit. Improved reusability. If you build a solid core networking module, you could potentially reuse that exact same module in multiple applications, maybe your main customer app and an internal admin tool without copying code. Make sense? How does it impact team workflows?
It enables parallel development. If Feature X and Feature Y are separate modules, Team X and Team Y can work on them largely independently, reducing merge conflicts and allowing faster progress. It also allows for safer dependency management.
How so?
Instead of adding a third-party library dependency to the entire application target, you can add it only to the specific module that actually needs it. This limits the scope of that dependency, reducing the chances of those diamond dependency conflicts we talked about earlier.
And testing.
Easier testing and CI. Modules, especially if well-designed, can often be tested in isolation. You can write unit tests for just the analytics module without needing to build and run the entire application. This leads to faster, more focused tests and potentially quicker continuous integration pipelines.
So modularization isn't just neatness. It's fundamental for speed, stability, reusability, and team velocity in large projects.
Couldn't have said it better myself. It's essential scaling hygiene. Now, related to performance and stability, the outline brings up something that isn't strictly dependency management, but is crucial in the Apple ecosystem. Automatic reference counting, ARC. Why is understanding ARC so important when dealing with all this code, both internal and external? ARC is the fundamental memory management system in Swift and Objective-C. It's how the system knows when it's safe to free up memory that objects were using. Understanding it is vital because memory leaks or crashes related to memory management are common stability-killing bugs.
How does it work? It's not garbage collection, right?
Correct. It's automatic reference counting. Instead of having a separate garbage collector process run periodically, ARC works differently. Every time you create an instance of a class, ARC keeps track of how many strong references are currently pointing to that object.
Strong references.
Yeah.
Variables or properties holding on to the object.
Exactly. When a variable holding a strong reference goes out of scope or is reassigned to nil or another object, ARC decrements the reference count for the object it was pointing to.
Okay, so the count goes up and down. What happens when it reaches 0?
As soon as the strong reference count for an object drops to 0, meaning absolutely nothing is holding on to it anymore, ARC immediately deallocates the object and frees its memory.
Immediately, not later.
Immediately and deterministically. That's the key difference from traditional garbage collection, GC, found in languages like Java or C#.
How does GC work, by contrast?
GC typically runs as a background process. It periodically scans the application's memory, identifies objects that are no longer reachable, and then frees them up. This process can happen at unpredictable times and can sometimes cause noticeable pauses in the application, the infamous stop the world GC pauses while it does its work.
So ARC gives more predictable performance because deallocation is immediate.
Generally, yes. ARC's overhead is distributed more evenly as references change, rather than concentrated in GC cycles. This often leads to smoother perceived performance, especially in UI-intensive applications. It's also generally lighter weight, as it doesn't require a complex background runtime process constantly scanning memory.
But ARC isn't perfect, right? What's the catch? The outline mentions strong reference cycles.
That's ARC's Achilles heel. A strong reference cycle, or retained cycle, happens when two or more objects hold strong references to each other, forming a closed loop.
Like object A has a property holding on to object B, and object B has a property holding on to object A. Exactly. Or it could be a longer chain. A points to B points to C, and C points back to A. In such a cycle, even if all external references to A, B, and C are removed, the objects within the cycle keep each other alive because their reference counts never drop to 0. They're artificially inflated by the cycle itself. And this causes a memory leak.
A permanent memory leak. Those objects and any memory they hold onto will never be deallocated for the entire lifetime of the application. Enough of these cycles and your app's memory usage will grow continuously, eventually leading to poor performance or even crashes due to memory pressure.
So how do developers prevent these cycles? This seems critical when combining code from different modules or dependencies.
You break the cycle by declaring one of the references within the potential cycle as either weak or unowned.
Okay, weak versus unowned. What's the difference? A weak reference does not keep the object it refers to alive. It doesn't increase the reference count. Importantly, a weak reference must always be declared as an optional type. For example, weak var delegate. My delegate. This is because the object it points to could be deallocated at any time if all strong references disappear. If that happens, ARC automatically sets the weak reference to nil. So you use weak when the other object might disappear first.
Right. When it's possible and legitimate for one object in the relationship to have a shorter lifetime than the other, think delegate patterns. Often the delegate is weak.
And unowned. An unowned reference also does not keep the object alive. Doesn't increase the reference count, but it's not declared as optional. It implies a guarantee. You, the developer, are asserting that the unowned reference will never be nil during its lifetime. It assumes the reference object will live at least as long as, or longer than, the object holding the unowned reference. What happens if you're wrong, if the object does get deallocated?
If you try to access an unowned reference after the object it points to has been deallocated, your application will crash immediately. It's faster than weak, no optional checking, but less safe if your lifetime guarantee is incorrect. You often see unowned used in parent-child relationships where the child logically cannot outlive the parent.
The connection to dependency management seems clear then. If a third-party library you import has bad ARC hygiene and creates retained cycles internally, or encourages cycles with your code,
then your application suffers the memory leak. You inherit the memory management quality, or lack thereof, of your dependencies. Choosing well-behaved dependencies and understanding how to integrate them without creating cycles, using weak or unowned appropriately, is crucial for stability.
Okay, we've covered a lot of ground. The tools, the concepts like Semver and ARC, the risks like transitive dependencies and security, the benefits of modularization. Bringing it all together, for developers who might still be using CocoaPods or maybe even Carthage, the argument for moving to Swift Package Manager seems pretty strong. Let's just summarize the key strategic reasons why the ecosystem is shifting towards SPM.
Yeah, the migration is definitely happening, and for good reasons that address the pain points we've discussed. First and foremost, it's that native support in Xcode.
It just works out of the box.
Right. No separate tools to install or manage, lower friction for new team members, less worry about external tool compatibility with Xcode updates. You trust the native toolchain.
And the big one for team collaboration.
No project file modifications. This is huge for veterans of CocoaPods. By not touching the .xcode project or forcing a .xe workspace, SPM essentially eliminates that entire class of painful merge conflicts related to the project.pbx project file. That alone saves countless hours and headaches on larger teams.
Plus the performance and architectural benefits.
Absolutely. It's generally lightweight and faster in terms of dependency resolution and build integration compared to the overhead CocoaPods sometimes introduced. The cross-platform support is increasingly important as Swift expands beyond just Apple platform, server-side, Linux tools, etc. SPM is the standard there.
Cleaner repos too.
Definitely. Cleaner Git repositories. You just have your package.swift and the package.resolve file. No massive pods directory to ignore. No extra workspace file. It keeps the project structure simpler and source control history cleaner.
Maybe better security posture.
Arguably, yes. Better security and transparency in some ways. Dependencies are fetched directly from Git repositories based on URLs and specific versions, tags, or commits. There's no central spec repository acting as a middleman like CocoaPods historically had, and if you build from source, you have more visibility than with opaque binaries. You still need to vet the source, of course, but the mechanism feels more direct and transparent.
So overall, it's seen as the more modern, integrated, less intrusive, and future-proof solution provided by Apple itself.
That's the consensus driving the shift, yeah. While CocoaPods still has a massive legacy and works well for many, especially Objective-C heavy projects, the momentum for pure Swift development is clearly with SPM. Community support is also shifting, with more new libraries prioritizing SPM compatibility first. #tag outro.
Well, this deep dive really underscores that choosing how you manage dependencies isn't just some minor technical detail. It's a fundamental architectural decision, isn't it?
It really is. It directly impacts your app's performance. Static versus dynamic linking choices matter. It shapes your team's workflow and efficiency. Avoiding those merge conflicts is key. And perhaps most critically, it defines a huge part of your application's security surface.
Yeah, those supply chain risks and hidden transitive dependencies, they're genuinely scary when you think about the potential exposure.
The whole landscape demands tools that give you transparency, speed, and control, integrated tightly with the native platform. Whether you're managing ARC's deterministic memory or navigating Semver's compatibility promises, it requires constant vigilance. Stability in a world built on dependencies doesn't come free.
Which leads us perfectly into our final thought for you, the listener, to mull over. We've talked about the significant, often unseen risks posed by transitive dependencies, and we know sophisticated supply chain attacks targeting exactly this vulnerability are becoming more common. If fully auditing every single line of third-party code is practically impossible, how should we, as developers and as an industry, fundamentally rethink our approach to trust?
Yeah. When you include any third-party code, open source or not.
If every import statement, every package dependency is essentially an act of trust, what kind of safeguards, maybe beyond just version control and basic scanning, do we need to establish to actually verify the integrity of the code we're pulling into our applications? How do we build a more trustworthy supply chain?
That's a profound question, something to definitely consider the next time you hit build.
Indeed. We'll leave you with that thought. Thanks for joining us on The Deep Dive.
See you next time.